Thank you for coming to this session at the 11th International Advanced Automotive Battery Conference. My name's Gavin Harper. I'm a Faraday Institution Research Fellow at the University of Birmingham on the ReLib project, which is looking at the recycling and reuse of lithium-ion batteries. And the theme of my presentation today is Beyond Comminution, Next Generation Battery Recycling, Leveraging Artificial Intelligence, Automation and Industry 4.0.
I'm part of the Birmingham Energy Institute, and within that we have the Birmingham Centre for Strategic Elements and Critical Materials, which is working on a range of projects concerned with materials criticality. One of those projects is the Faraday Institution's ReLib project on the reuse and recycling of lithium-ion batteries. It's from that project that a lot of the research that I'm going to talk about today has come from. There are any number of projections and predictions, you can take your pick, about the growth of lithium-ion battery production in the years to come. What's a little bit more challenging is forecasting when those libs will reach the end of their life, given the potential for those libs to be used in second life applications after they've enjoyed a first life in electric vehicles. So we often talk about the waste management hierarchy, with prevention coming at the top, so if we can avoid creating waste in the first place, and then following that, reuse, recycling, recovery of energy, and then finally disposal as a hierarchy of options in terms of waste disposal. Now, within recycling, what I want to cover in this presentation is that there are a range of processes, from present battery recycling, which is focused around shredding and comminution of cells to passivate them, and often techniques like pyro and hydrometallurgy to recover the materials. But what we want to move towards is more advanced battery recycling processes with less manual labour input, more automation and artificial intelligence. That means that the complexity of the process is going to increase, but the benefit of that is that we might be able to extract purer material streams which are of a higher value and retain more of the energy that's been input into producing those material streams in the first place. And our hope is that we can increase the amount of materials recovered and the value of the materials recovered. So lithium-ion batteries are quite a complicated structure compared to, say, for example, lead-acid batteries, which are very simple and enjoy high recycling rates at the moment and high recovery rates of materials. There's a lot more complexity to lithium-ion batteries in terms of their structure, which makes them difficult to recycle. And there's also a great deal of variation in the chemistries that are employed by different manufacturers, and also the packaging designs of electric vehicle batteries. So there are different types of cells. There are pouch cells, which are sort of flat plastic laminated together with the layers of material inside. Prismatic cells, which have a rigid outer case containing the battery, and cylindrical cells, which obviously we're quite familiar with their use in portable electronics, and the sort of cells that are employed by Tesla and some other manufacturers. And what we envisage is a circular economy for electric vehicle batteries, where perhaps midway through the life of the electric vehicle you might extend its life with a reconditioned battery pack, and then at the end of life we deal with batteries intelligently, trying to extract the most value out of them. So considering whether the pack can be remanufactured into a new electric vehicle pack, have a second use in an application like stationary power storage, or if we need to recycle the pack and recover the material. And if we are going to recycle it, we want to do it as intelligently as possible, using processes that seek to recover as much of the material and value as we can. If we want to optimise the materials that we recover and to be able to separate battery packs and diagnose which batteries are suitable for reuse, remanufacture and recycle, we need to be able to break the packs apart and disassemble them. And at the moment this is being done manually, but as I've said earlier, we want to move to more automation as part of that process. And there are different challenges at different scales of the problem. So in terms of actually removing the pack from the vehicle in the first place, it's obviously something that is very physically heavy, so there's manual handling considerations around the weight of that pack. There are high voltages present, but also there's variation as a result of the vehicle service life. So different vehicles, different shapes and sizes, but also we don't know what's happened during that vehicle's lifetime. It may have been involved in a crash which has warped the chassis, so the bolts are in slightly different places or jammed or misaligned. There's a lot of variety in the different fixings. A mechanic may have tried to fix something over the years and ended up rounding off the bolts, or they might be rusted or corroded. And so there's a lot of variety to deal with, which is less of a challenge for a human, but if you want to automate that process, you're going to need some really smart robotics. Then once you've got the pack out of the vehicle, there are other challenges at the next scale of disassembly, taking the pack apart. So for example, there are lots of wiring looms within battery packs, and because wiring looms are flexible, they aren't always in the same place. So that presents a challenge for the robot because you need to employ a bit of autonomous decision making, artificial intelligence, machine vision, because you can't necessarily go to the same place and perform a prescribed motion. You need to be able to look at that pack and intelligently decide and plan the path that the actuator is going to take to manipulate that wiring loom out of place. And so there are different things we might be able to do in the future to design for disassembly, so maybe replacing flexible wiring with buzz bars or rigid connections. And there's a whole series of challenges around data, so we don't know what condition the pack is in, we don't know what's happened during its service life, what sort of chemistry is in the batteries that that pack contains. And so there's a real opportunity for design for recycling, including data, maybe having like a digital passport that accompanies the battery pack that contains information. And it could be that that passport is dynamically updated with information from the vehicle during use from the battery management system. So at the point of disassembling the pack, there are also lots of hazards around the potential for off-gassing, fire and thermal events, and also thinking about the actual process of disassembly. So for example, if you're using a metal tool and you drop that and that creates a short circuit, there's obviously problems there in terms of a thermal event. It's easy to explain that to a person, but as far as robotics are concerned, how do you develop robust mechanisms and algorithms to ensure that as things are manipulated, metal tools can't become dislodged and drop into that pack?
So we've got a paper that's currently in press that has been submitted to the journal Resources Conservation and Recycling. And that paper is looking at whether to shred or not to shred as a preliminary cell breaking step before subsequent processes. And it's a techno-economic evaluation of a range of different hydrometallurgical process routes for treating lithium-ion battery waste. And it compares what happens if we used sort of mixed black mass as a feedstock versus what happens if we've disassembled the cell prior to hydrometallurgical processing. And obviously, if we can disassemble the cell first of all, then the streams of waste that are going into that process are much more refined, they're not mixed, and they're easier to separate. And the upshot of that review of a range of different processes is really that if we can disassemble the cells first of all, it results in much more efficient and economic subsequent processing of the lived waste.
And so I would characterise the two different approaches in terms of shredding versus cell disassembly as really being a tension between the mechanical complexity of the separation step versus the chemical complexity of what comes next. So in shredding, it's very simple mechanically. The cells and the modules get fed into a shredder, they get made into a black mass. But then the chemistry that has to then follow from that is much more complicated because of the mixed feedstock and everything being jumbled up together. Whereas if we could move to a process where the mechanical pre-treatment stage was perhaps a little bit more difficult and involved, it might result in much simpler chemistry down the line, which could lead to either better hydrometallurgical or potentially direct recycling routes. Now, if you look at where we are today with the state of the art of a range of different lithium-ion recycling technologies, and we cover this in our Nature review, which looks at lithium-ion battery recycling, there's limited potential to improve pyrometallurgical processes. However, there's a great deal of potential to improve hydrometallurgical processes, and direct recycling is another technology that shows a lot of promise that could be enabled by cell disassembly.
The real promise of an automated Industry 4 approach to battery recycling isn't just in removing the labour content of taking the batteries apart and separating the components. It's also in the potential for integration with data management around battery management systems and potential future systems around, for example, blockchains related to battery components. And this really allows us to manage the asset more effectively. So at the end of a battery's life, the process of gateway testing and triage of batteries becomes much more efficient, and that's something that's currently very manual and labour intensive. And the data management that could come from extracting information automatically from battery management systems or blockchains related to batteries, allowing for automated fault diagnosis and repair of battery packs, replacing components, returning batteries to service, and then removing the discarded components for recycling streams. And then also being able to manage the asset data around, for example, the cathode formulations, so that when batteries enter that disassembly process, batteries of a similar type can be sorted together automatically, resulting in a purer output stream of material for subsequent hydrometallurgical or direct recycling processes.
Within the ReLib project, the robotics theme is led by Professor Rustam Stolkin, who's head of the Extreme Robotics Lab, assisted by Dr. Alireza Rastagarpanar, who is a Faraday Institution Research Fellow. And one of the main themes that they're looking at is how can you use cheap, off-the-shelf industrial robotics hardware and augment it with clever artificial intelligence to really add value. So they're breaking down the range of tasks that you might encounter when processing end-of-life vehicle batteries and developing solutions for different parts of the problem. So for example, how can you get a robot to make contact with the battery to enable EIS testing to ascertain the state of health of the battery? Other challenges they're tackling include using vision-guided manipulation, so we can imagine situations where we have cobots, that's robots working in collaboration with human operatives, and how can they assess a situation using vision systems to ascertain the position of objects and also operatives that may be collaborating with the robot.
Which takes me very neatly onto our next slide, the University of Birmingham's plan for scale-up and demonstration. So the University of Birmingham's made a big investment in Tyseley Energy Park, which is going to be a centre for demonstration for a range of different energy technologies near the centre of Birmingham. And there's a whole host of different technologies that are going to be deployed on that site. But one of the things that's interesting from a battery recycling perspective is the Birmingham Energy Innovation Centre, which is going to be a hub for some of our work around critical materials amongst other research. And within that building, we're going to look at developing an integrated approach to electric vehicle recycling, leveraging a lot of our work around robotics and automation to look at both how to recycle electric vehicle batteries and remove those from vehicles. But also there's another stream of work at the University of Birmingham that is looking at how to take electric vehicle motors and how to recycle the neodymium rare earth magnet from them using a novel process that's been developed and patented by the university. So there are some similarities between recycling electric vehicle motors and electric vehicle batteries. And if you think about the challenges at different scales of disassembly, so removing the motor from the vehicle, then being able to take the motor to bits, then being able to extract the magnetic material, there's actually lots of commonality there. So in terms of some of the manual handling tasks for removing the motor, in terms of some of the challenges around the diversity of different designs, the weight of the motor, the physical bulk of it, and then as you start to take things apart around being able to dismantle cable looms, and then when it comes to the actual motor itself, you know, the use of glues and adhesives to hold magnets in place. There's similarities there with some of the challenges with glues and adhesives in electric vehicle batteries, and of course the opportunity for design for manufacture. But as I mentioned earlier, there's this proprietary process that's been developed by the University of Birmingham that is able to decrepitate neodymium rare earth magnets to make the magnetic material easy to recover and to turn into new electric vehicle motors. And our aim is really to take an integrated process to the dismantling of cars. And if you look in this next short video, you can see our approach. So rather than the sort of production line approach where you've got a sequence of robots, one after the other, performing an action, we believe that actually there's such a diversity of vehicles to deal with that actually you may be better off tackling that at one station with flexible robotics that are able to change their tooling and adapt to different vehicle configurations and geometries. A theme that's come up a couple of times in this presentation and is something that I think the industry really needs to give consideration to is how might we design lithium-ion battery packs better to enable recycling, so design for recycling. And I think some of this could be around standardisation, so the less variety that we have to deal with when recycling battery packs, the easier we can recycle them. Some of them is also about conscious design decisions, so making things easy to take apart, perhaps reducing the variation in the types of fixtures and fastenings that are used within that. Also thinking about the elimination of glues and adhesives, thinking about how we can maybe have mechanical fixings rather than sticking things together. And I think some of the same challenges for designing lithium-ion batteries for recycling we could also apply to electric vehicle motors around that standardisation, removal of adhesives. And I think also there's an opportunity in terms of that communication of data between the product and the recycler to be able to identify components which will optimise the way in which we're able to recycle them. It's an exciting time at the University of Birmingham as despite all the challenges that have been presented by the pandemic, work has continued apace on the construction of the Birmingham Energy Innovation Centre, where we're going to trial some of these novel recycling approaches.
I hope you enjoyed the presentation. My contact details are on the next slide, and I would love to hear from you if you've got any further queries, questions, if you'd be interested in collaborating with our project or finding out more about our research. Please get in touch.